is the trivia session. And basically, let's have a quick series review. So we've had 7 sessions so far. And the first session, we spoke about all the basics of ML. Second session, we focused on regression and classification. Third session, we focused on naive Bayes and SVM. Fourth was all about decision trees as well as random forest. Fifth had things about evaluation metrics as well as unsupervised learning. Sixth was about ensemble learning techniques such as bagging, boosting, stacking, averaging, and things like that. And the last session was just a brief introduction to neural networks as well as deep learning. All right, so let's get started with our quiz. So now this is a quizzes link. So this is the link to the quiz, which I'm sure all of you would have already gotten in the chat. So once you open that link, please enter your full name. Why we're asking for your full name is that it will be much easier for us to track your scores on the leaderboard, as well as give you a shout out on our socials when your full name is entered, so we know exactly who to identify. So now this is an instructor-led quiz. What does that mean? That basically means is that I will be leading the quiz. So for every question in this quiz, you will have 1 minute to answer. It's all just theoretical question. There is no math involved, just theory based on all these 7 sessions that have happened so far. And in these theory questions, most of the questions are like multiple choice. You have a couple of questions that are also fill in the blank. And you'll have 1 minute to answer these. And by an instructor-led quiz, what I mean is that once I finish one question, only when on my screen I move to the next question, will you be able to move to the next question on your screen as well. So until then, it'll be on the same question. So after every question, we'll have a discussion on why that particular answer is the right one and why the others are wrong. And only then will we be moving on to the next question. So we have 25 questions in total. 1 minute to answer each question. So once suppose you're on the first question, you have a minute to answer that question. Once the minute has expired, I will be discussing the answers for that particular question. And if you have any doubt, do enter it in the Q&A box. And once we've discussed the answer and come to a conclusion there, we will be moving on to the next question. So only when I move on to the next question, will you be able to see the next question on your screens as well. So it'd be great if you could join this link. I think it's already been posted in the chat. So do click on that link and enter your full name so that we can keep track of you on our leaderboard. So let's get to the quiz. So I see like there are around 6 people here. So like, I think there are around 20 attendees and 7 panelists. So 6 panelists. So whoever wants to join, do join. So once everyone joins is when I'll be starting the session. The link is in the chat. So if anyone has any problems, do like put it in the Q&A box or the Zoom chat. So please do join in. So let's all have fun together. I'll just wait for maybe another minute. So like there are total of like 19, 20 attendees and there are only 9 people here. So I'll just wait for another minute. It's all right if this is actually the first session you're attending as well, because either way, we'll be discussing the answers to every single question. So this will definitely be a refresher of many ML concepts for all of you. So even if you're a newbie to ML, it'll be great if you could just join. And even if you get like 0 on 25, that's still okay, because you'll definitely be able to learn something here. So I'd encourage all of you to. All right, so Teresa says that she won't be able to join the quiz. That's okay. Hopefully you somehow still learn something from this session. Yeah, it's not meant to be competitive. We'll just have some fun and, you know, see some answers. It's just going to be like a fun activity. So Sonal asked, we need to input the game code somewhere. You don't have to, you can just join that link and that link will directly take you to the game. All right, maybe I'll just wait until it's like another minute more. So like again, like Zareen also mentioned, this is not something for competition. This is not something where you'll be judged based on how much you get or your scores and things like that. This is just something that's fun and a place where we can like refresh on some very basic ML concepts that all of us tend to forget. So yeah, so just attempting it would be quite fun and quite nice. All right, just we'll be waiting for another. Yeah. Okay, then I think we can get started. So does anyone want me to wait for another minute? Is anyone still setting it up? All right. Okay, then we can get started. So I'm going to start. And once I click on the start button, the first question will appear. So just take a minute to answer that question. Once the question is done, we'll be discussing. So I think once you do a couple of questions, you'll be able to get the flow. So let's get started. All right, so we have quite a few people who got this right. And the answer, as most of you have answered, is supervised learning. So the question says, what type of machine learning algorithm makes predictions when you have a set of input data and you know the possible responses? So the fact that they mentioned that you know the possible responses, that means that it's labeled data. So you, in a labeled data is when you know the possible responses and you're able to train your machine in that way. So that is why it's called supervised learning. So if you have any other follow-up questions as to why it's supervised learning, or if someone didn't understand, you can definitely ask in the chat and I'll get back to you. All right, that was great, everyone. And moving on to the next question. Woo, okay, that's great. So I see that most of you again have answered the right one. So really happy and proud of all of you. So I'll go to this full question view. So it'd be great if all of you could come to my screen for a moment. All right. So the question is, what is overfitting? So the first answer for that is, when a predictive model is accurate, but takes too long to run. So that's definitely not overfitting. Overfitting is a case where a machine learning model, what happens is that it learns so much about the training data that it learns all about the noise as well. And when you apply it to a testing data, it does not perform that well. It's kind of like, let's say for a test, you have chapters one, you have just, you understood that you have just chapter one. So you mug up everything in chapter one. But the teacher asks you like 75% questions from chapter two. And you just like briefly went over that. You do not know what's chapter two. You learned only chapter one. So when it's about something about chapter two, you will not be able to answer that question because it's not, you're not generalized. You only know one particular thing. You've just focused on that, mugged everything up. So that's what overfitting is. It learns way too much about the training data that on the testing data, it's not able to perform. So option one does not imply that. Option two is when you use deep learning for a machine learning problem. Doesn't make sense. Let's go to option four. When you perform hyperparameter tuning and the performance degrades. So hyperparameter tuning is something we do in deep learning, where we change some things known as hyperparameters, and those things help us make our deep learning model perform better. The performance never degrades, like it rarely degrades when you do tuning. It actually becomes better. So the third option is the right one. That is when the model learns the specifics of the training data that can't be generalized to a larger data set. It learns so much about the specifics of the training data that you cannot generalize it to a larger data set. So that's about overfitting. Again, if you guys do have any questions, do put it in the chat. So
Sneha, can I just interrupt for 1 minute? So I think
sure.
few attendees are having some issue that, so one person, she I think mistakenly just closed the tab and now she cannot rejoin. So is there a way that she can join again because the quiz has started?
Oh, I don't think so. The thing is, I'll have to end the session for them. I mean, that's why I was mentioning, I don't think I can like in the middle like that. Okay, maybe what you could do is whoever is like unable to join, right? Could you like put your answers in the chat? Like whoever hasn't joined yet and is unable to join, just put your answers in the chat. What I'll do is I'll maybe take a notebook and a pen. I'll note down your name as well as your answer so that I can include that in the leaderboard as well. Is that cool?
Yeah, I think let's do that.
All right. All right. So I think there's,
thanks,
I'm not sure if I'm pronouncing this right, but Ekaterine, there's Stacy as well as Jessica. So I guess all of you could enter, all of you could like put in your answers for the particular questions in the chat and I will go through them. So hope that's okay. All right. All right. So hope this was, people understood this. If you have any doubts to ask, and let's move on to the next question. All right, our leaderboard's looking great. And okay, wow, we have an equal answer for train as well as fit. So I mentioned the common command used to train an ML model in Python is model.fit. So in Python, we do not have a command called train. So it's always model.fit. And in fit, so fit is basically a function. And to that, what you pass to is your X train as well as Y train. That is basically your training data set. So you'll always say model.fit and you'll include your training data set. That's the X train and the Y train. In case of like supervised learning, you have all the features as well as the label. So the features will be stored in X train the label will be stored in white train. So it's always model.fit. So that was just a question on ML command. So let's move on. Okay, wow. So the leaderboard stayed constant for this one. And okay, well, most people actually answer this right, and that's amazing. The answer is feature selection. So the process of identifying significant features from a set of features is called feature selection. So let me go one by one. Dimensionality reduction is basically you have a lot of features and some features are quite similar to one another. You don't want to train on so many features, because if you train on so many features, what happens is it will become very complex and it will take too much time to train. So in that case, you want to reduce the number of features. So you want to do some dimensionality reduction, and basically it's like an algorithm. So you use algorithms like principal component analysis to do that. Now, feature extraction is not the same as feature selection. Feature extraction especially is the process of extracting the features you require. It's especially used in deep learning, where in deep learning, each layer of that neural network, what we do is that we use a single layer to extract some features about that data and understand it. But to identify significant features, that is feature selection. So there's nothing called feature intuition. It's called feature selection. So the process of identifying significant features is feature selection. In deep learning, especially when you want to extract features to finally predict your output, that is feature extraction. It's also used in machine learning. Dimensionality reduction is when you have many similar features and you don't want to use all of those features. So you reduce from like 30 dimensions to 2 dimensions. And for that, you use algorithms like PCA, principal component analysis, and things like that. So that's about this. Again, if you do have any follow-up questions, please do ask in the chat. I'll help you out. Let's move on. All right, so I guess the leaderboard staying constant for that. And yes, so most of you have clicked on the correct answers. The places where we require machine learning are face recognition, as well as the music recommendations you get on Spotify. So these two things are what work on machine learning. Now, feeding a baby does not really require machine learning. It's just a manual task that we do. Now, let's say you have the task of watering plants every day at 1 p.m. Even if you do want to write a computer program to do this, like let's say you have a can and you want to write a computer program that simulates this can, if it's still just at 1 p.m., there are just a couple of rules it needs to follow. It just basically needs to water the plants that are present at 1 p.m. So you can set that timer and it has to water the plants. So that really does not require machine learning. Again, it's quite a manual task. Either we do it manually, even if you have to write a computer program for it, there is nothing that a machine can learn to do this task. It just has to follow two rules. At 1 p.m., pour the water at the given plants. So these two do not require machine learning. They're just manual tasks, while these two do require machine learning. So glad that most of you got that right. And let's move on. Oh, nice. So we have some change in our leaderboard. And all right, so most of you have given AI, which is absolutely correct. So if you remember from our very first session, we learned that the subset goes like this. We have AI, which is the biggest umbrella, and a subset of AI is machine learning, and a subset of machine learning is deep learning. So AI is the umbrella where what is AI basically? AI is where you want to automate things. You want to automate things in a way, similar to the way that humans do things. That's what AI is. You want to find means to automate things. Now, machine learning is the algorithm that enables a machine to learn on its own without having to be explicitly programmed. So you don't have to explicitly sit and program these machines. They will learn on their own. But if you just give them data, they will learn on their own and understand the pattern in that data. That's machine learning. Now, deep learning, basically, it tries very much to model how the human brain works. So it also has the concept. So in our human brain, we have many neurons that are connected with one another. So deep learning has artificial neurons. Now, why do we use deep learning when there's machine learning? Well, deep learning can handle tougher data. Like when there are so many features that you need to extract, machine learning may not work well, especially if you take like image recognition problems and things like that. Not just image recognition, any problem that has way too much data and there are way too many features that you can extract, you send that to deep learning so that deep learning performs a better job. So this is how it works. AI, subset of that is machine learning, subset of that is deep learning. Now, data science uses AI, machine learning, and deep learning, as well as mathematics, statistics, and things like that. So it's an overlapping section, not a subset of anything. So hope that helped. Let's move on. All right, amazing. And okay, again, most of you have answered this right. So I'll just go to this interactive whiteboard to explain this question better. Now the question is, what is the maximum depth of a decision tree? So, am I not able to draw? Yeah, okay. So a decision tree basically looks something like this. I apologize for my bad drawing. I just want to explain what it looks like. All right. So just imagine you have a decision tree like this. This is known as the root node. And this is a subnode. A node that's in between is just called a subnode. And this final node is known as the leaf node. All right. So the maximum depth of a decision tree is always the length of the longest path from the root node to the last leaf node. So to the leaf node is always the node at the end. So from the longest path from the root node to the leaf node, that is known as the maximum depth of a decision tree. Sorry. So the maximum depth of a decision tree is the length of the longest path from the root node to the leaf node of a decision tree. So yeah, I guess most of you got that. The length of the longest path from the root to a given subnode. So that is not a maximum depth. That is some depth, but that will definitely not be a maximum depth. The maximum depth is always from the root to the leaf of a decision tree. So hope that helped. Let's move on. All right, so we can see some change in the leaderboard again. And all right, so again, amazing that a lot of you got this correct. So suppose in a classification problem, you're using decision tree and you use Gini index as the criterion for the algorithm to select a feature for the node. So the feature with the dash Gini index, okay, let me go to full question. Yeah, the feature with the dash Gini index will be selected. So it's always the least. Let me tell you why. Now, Gini index basically measures the goodness of a feature. So let's go back to the whiteboard and my terrible drawing. All right. So suppose you have a tree like this. Suppose, okay, so based on this factor called Gini index, let's say you're choosing a feature. Let's call this, let's say the problem you're trying to deal with is predicting if a person has a heart attack or not. And you're trying to use Gini index as a factor, and you basically select chest pain. You select this feature called chest pain, let's call it C. And using this chest pain or C, you're trying to classify the data points as whether heart attack or not a heart attack. So now, if it's able to do classification in this manner, that is most of the, so let's say you have 5 data points here. Out of that, 4 have a heart attack and 1 does not have a heart attack. And here, let's say all 5 does not have a heart attack. So here 4 have a heart attack and this is don't have a heart attack. And here all 5 don't have a heart attack. So you can see that this feature was able to separate the classes well. It was able to separate the classes. It was able to separate the data points well into the separate classes. That is, when you use chest pain as a feature, you were able to split your data points. You were able to understand that, okay, so the people who do have a chest pain will have a heart attack and the people who don't might not have a heart attack. So you were able to split your data points. So when it's chest pain, and you were able to split it as one particular class and another particular class. And there was not a lot of mix of class. You were able to clearly see that if yes, then 4 people had a heart attack, 1 didn't have. That's how it is classified. And if no, then 5 people did not have a heart attack. So this chest pain proved as a good measure for you to classify this. And when does this happen? This means that chest pain was a good metric for you to classify pure nodes. Pure nodes means that there were not much mix in the final classification. So a lower Gini index will help you get a pure node. So when you have features, when you're selecting features for a decision tree, and you're calculating the Gini index of these features, the one that has the lowest Gini index will always be on top of the decision tree, because that is what will help you classify the data points best, because you get more purer nodes. That's why the feature with the least Gini index is always selected. Again, I hope that helped. If any of you have any follow-up questions about Gini index or decision tree, do ask it out in the chat. Let's move on. All right, so again, we constantly do keep getting some changes, but I think the top few scorers are constant. All right. So, okay, so most of you would put training or test set, but the actual answer is task. So let's understand this. So Tom Mitchell, he was a machine learning and data, like AI engineer, and he basically defined machine learning as a computer program that is set to learn from experience E with respect to T. Now, T is something you don't know. In the actual definition, T was mentioned, but I removed the mention of that just to help you understand and figure out, because this was like an intuition based question. Basically, you know what machine learning is. So based on this definition, what do you think T could be? So computer program that is set to learn from experience E with respect to T and performance measure P. If its performance in T as measured by P improves with experience. So that means that it learns with experience with respect to something, and it tries to measure its performance in that particular something. So it could be training or test set, but those are not the only types of data sets that we have. We also have a validation set, right? So the main thing is a task. You are given a particular task. So your task is, so a training or test set is not your final goal. Your final goal is whether it's performing well in that task that it's given. So that task could be classifying apple from an orange, classifying a cat from a dog, recognizing the image of someone's face. So from the experience, that is from the given data, if it's able to learn from experience and perform a particular task, get a good measure of P, which is the basically performance measure, then it's said to be machine learning. So there, it's not training or test set, because you have 3 types of sets. You have training, test, and validation. So what actually fits this definition is task. So with respect to a particular given task or a goal that you want to achieve, if your computer program did well by learning from experience, and its performance can be measured using a performance measure P, then it is known as machine learning, and the T here is called task. So I hope that helped. Let's move on. All right. So it's wonderful. Most of you have gotten this answer, right? It's KNN. So let me just explain KNN with a simple example. I'm going to explain how KNN works with a simple example. Now, let's say that you have, let's say in your hands, you have apples or on a, basically on, okay, let me just go back to the whiteboard again to help understand better. All right. So imagine you have to classify in this manner. You have some stars here. You have some circles over here. You have some circles over here. And then there is a new data point over here. Okay, let's draw it in a block. Okay. So now what KNN does is that it looks at the nearest neighbors. The K stands for the number of neighbors. So let's say it looks at the 3 nearest neighbors. So one nearest neighbor is here, another nearest neighbor is here, and the final nearest neighbor is here. So to the KNN algorithm, we have already classified. We already know, the KNN algorithm already knows that there are 2 different classes. So when a new algorithm comes, all it has to do is look at the nearest neighbors. It's not really learning anything here because it's just already we've given, it's a supervised learning algorithm. So the classes are already separated and given to it. So when the classes are already separated and given to it, and when there's a new data point that comes in, it just looks at the nearest neighbors. So in this case, when it looks at the 3 nearest neighbors, it understands that the maximum was star. So this point also becomes a star basically. And when this becomes a star, so that's what you classify it as. You classify it as a star over here. So now that you've classified it as a star, you know that the algorithm is not really learning much because you already have the classifications given to you. It's a supervised machine learning algorithm. The classifications are already given to you. All you have to do is take that new classification, look at its neighbors, and put it where the neighbor is. So you just got to learn what the neighbors are. So you're not learning a lot as compared to other algorithms in the training process. You have the classifications given to you, just got to look out for the neighbors. So that is why it's known as a lazy learning algorithm. All right. Any other follow-up questions? Do ask me, and let's move on. All right. So, okay, that's amazing. So most of you have gotten this correct. So let's go to the full question view to actually see it. So what does a decision tree do? And the answer is maximize the information gain and minimize the entropy. So information gain is something like this. When a decision tree goes from one level to another, it's supposed to do some sort of classification and understand the features better. That's what information gain is in a nutshell. Now, entropy is randomness. You do not want a lot of random data when you like a lot of random data in the sense that when classification of the data points are happening, you do not want like suppose you're classifying as heart disease and not heart disease. You do not want both the classes in one node. You want the classes to be split apart. So entropy means randomness. That is, both classes will be present in one node. Like both the classes will be present in one node, and that would mean that it's quite random. You're not able to figure out if it's class A or class B, if it's heart disease or not heart disease. Let's say there is no majority like in the previous example. Both classes are present in that one node, and you're not sure which one is higher, which one is lower. So there's some sort of discrepancy there. And because of the discrepancy, you're not able to figure out which class does it belong to based on this feature. So what you're trying to do is maximize the information gain. When you're moving from one level to another, and that is when you're moving from one level to another in a decision tree, you're basically moving from one feature to another. So when you're moving from one feature to another, Your aim is to learn more. So that is information gain. And entropy is when you're moving from one feature to another, your classification is supposed to become clearer, not more confusing and more random. Therefore, you have to maximize the information gain while minimize the randomness or minimize the entropy. So I hope that helped. Again, any follow-up questions, do ask me. Let's move on. All right. So can we perform linear regression with a neural network? The answer is yes. Neural networks can be used for regression as well as classification. So if your final output basically has to print out some numbers, then it's a regression task. So definitely neural networks can perform regression. If your final output of a neural network is to put it in a particular class, then it's classification. If the final output of your neural network is some sort of numbers, some integer value, like let's say predicting the weather or predicting house price and things like that, and suppose you're using a neural network for that task, you can definitely use, you can definitely model it as a regression problem. So yes, we can perform linear regression with a neural network. So I hope that helped. Let's move on. All right. So again, most of you have gotten this, and that's so amazing, guys. All of you are really doing so well, and that's great. So big pat on the back for all of you and huge claps. And yes, the answer is reinforcement learning. So let's read this and understand this problem. The robotic arm will be able to paint every corner in an automotive part, in the automotive parts, while minimizing the quantity of paint wasted in the process. Which learning technique is this? Now, when you have to think about supervised and unsupervised learning, it's very simple. Why is it very simple? Because in supervised learning, you have labeled data. Unsupervised learning, you have unlabeled data. Supervised learning, there'll be some sort of label that's attached with the data that's given to you. For example, you're giving a machine images of cats and dogs, and you've already pre-labeled them. Then it's a supervised learning. Suppose you're giving a machine an image of cats and dogs, but you've not labeled them before, and you want to classify that. That's unsupervised learning. But things like this. So if you look at this a task exactly, think of humans doing that. So maybe like if, okay, so suppose it's your first painting job, like you're giving a job to paint something. It's your first painting job. Maybe you won't do it very well. Maybe you've used up too much paint, you've not done it properly and things like that. But as you keep repeating and repeating, you'll be able to learn better. So that is what reinforcement learning is. Reinforcement learning is basically learning from doing it over and over again. It's like learning from experience, learning from the environment. So in reinforcement learning, what we do is that when a model does reinforcement learning, it first starts off doing some things, some random things. And whenever it makes a move, whenever it takes some sort of action, we give some reward to it. A kind of like, let's say you're training your dog to get the newspaper every morning. So initially, when the dog doesn't do it, or when the dog doesn't do it properly, you don't give the dog treats. But when the dog does get the newspaper properly, you give the dog treats. So those treats act like little rewards for the dog. So when the dog realizes that every time it gets the newspaper properly and correctly, then it's going to get treats. So it's going to do it more often. It's going to do it right because it understands that it's going to get a reward. That's how we train reinforcement learning. Very similar to this type of training, very similar to how humans learn. Learns from experience, learns from the environment, and is able to, do some optimization tasks. So here we're asking, while minimizing the quantity of paint wasted in the process. So that is what your objective is. You want to minimize the quantity of paint. So when the robotic arm is able to minimize the quantity of paint, we'll be able to give it some reward. So that's why it's a reinforcement learning, because you have some sort of task, learning from environment, and you're giving it a reward for performing that task. So again, if you have any follow-up questions, do let me know. I'll type out the answer in the chat, or I'll answer it live if there's a time. So moving on. All right. So which of the following is not true about ensemble learning techniques? And this was a multi-correct question, but I just given that to confuse, because when you read a question and you're like, okay, select all and apply, your brain is tuned to think that, okay, there's definitely going to be more than one correct answer. Otherwise, why would they have given it a select all and apply? But actually, there's only one that applies, which is option D. So which of the following is not true? That means which of the following is false about ensemble learning. So the first option is bagging decreases the variance of the classifier, and that is absolutely true. So in bagging, what do? We have, let's say, some data. We take subsets of that data. Those subsets are passed through different algorithms, and we aggregate the result. So since it's passed through different algorithms, you're generalizing it. Therefore, when you generalize things, the variance of the classifier decreases. Now, boosting helps decrease the bias of the classifier. So what you're doing in boosting is that you're focusing on simply the errors. Suppose you have some data, you take a subset of it, run it through one algorithm. The errors of that is taken and given to a second algorithm. The errors of that is taken given to the third algorithm. So there you're focusing more on the errors. So that helps you reduce the bias, because you're trying to learn the patterns in the data. You're trying to understand what's happening there. So that helps you reduce the bias. So that's what boosting does. And bagging does combine predictions from different models. So like I mentioned, in bagging, you take a subset of the data, you give it to different models, and the final result from all those models is aggregated. You either do max voting, that is take the maximum value, or you do some averaging techniques. Now, the wrong answer is that bagging and boosting are the only available ensemble techniques. No, that's absolutely not true. Even in the session about ensemble learning, we learned stacking, we learned averaging, we learned max voting. These are all ensemble learning techniques. Bagging and boosting may be the most popular ones, but others are also there. And there are many other ensemble learning techniques. So hope that helped. Let's move on. All right, so we have some small changes in our leaderboard. And the correct answer for this question is generative. So a generative model, okay, so naive Bayes is a type of classifier. So if you have 5 classes in naive Bayes, what naive Bayes tries to do is that it learns everything about these classes. And then when you get a new data point, based on what it learned about every single one of these classes, it classifies it there. So that's called generative learning. In generative learning, you have some classes that you want to classify a data point into. You learn every single thing about those classes and then you classify it. But discriminative learning is not like that. Discriminative learning is you have class A, class B. You understand some like what makes class A different from class B. That's all you learn. Okay, so this is kind of like you want to distinguish between a lion and a giraffe. So generative learning, what will do is learn everything about the lion. Okay, what does it have? What are all of its features? Every single possible feature of a lion to learn. And learn every single possible feature of a giraffe as well. And then when you get a new image for that model, it will look at what it's learned. And then based on what it's learned, it will put it as either lion or giraffe. But discriminative learning, what it does is that it just looks at the differences. So it looks at, okay, giraffe has a tall neck and the lion has a mane. So it looks at these differences, doesn't necessarily learn all the features, just looks at these differences. It discriminates there. And then it's able to classify a new data point. So naive Bayes is example of generative. Let's take SVM, support vector machines. That's an example of a discriminative classifier. Again, if you have any doubts, do ask me. Let's move on. All right, wonderful. Okay. In SVM, what are support vectors? So most of you have gotten this right, and that's amazing. So let me again just draw a diagram to explain what SVM looks like. So in SVM, you have something like this. This is known as a decision boundary. And these are some dotted lines. Let's say these small lines, let's assume these are dotted lines. Now let's say there's a class here. So let's say it's stars, and here there are circles. So the points, those data points that lie closest to the decision boundary. So let's say it lies here, it lies here. There are some stars over here and over here. So the data points that lie closest to this decision boundary actually help determine where the decision boundary is. You want a decision boundary such that it has maximum distance here, maximum distance. So this distance between the support vectors, that distance is called a margin. You want to put a decision boundary in such a way that it maximizes the distance between the support vectors. That is, maximizes that margin, So the place of the support vector is very important. And the data points that are closest to the decision boundary are known as support vectors. These are the ones that help you determine the decision boundary. So I hope that helped, I think. Yeah, I'll just answer this question live. So Rupal's asked, can you explain why SVM is a discriminative classifier? Now, like I mentioned, discriminative classifier is one that just discriminates the two classes, does not necessarily need to understand anything. So in a discriminative classifier or in SVM, if you see, you're just trying to look for a decision boundary that separates the class. You're only looking for a means of separation. If you look at naive Bayes, if you have naive Bayes, you have 10 features in naive Bayes. Naive Bayes applies something known as the Bayes algorithm or the Bayes theorem. And using the Bayes theorem, it's able to understand everything about that class. It's able to like it's a probabilistic model. So it's able to understand everything about that class, and then it classifies a new point. So when it's able to understand everything about that class based on Bayes' theorem, then it's known as a generative thing. But in discriminative classifier, SVM, it just tries to draw a decision boundary between two given classes. Does not necessarily learn everything about it. There is no probabilistic model learning everything. Just a decision boundary that's trying to separate the two classes, having maximum margin. So that is why SVM is called a discriminative classifier. I hope this helped. If you still didn't understand, do ask again in the chat. All right. So I hope you understood what support vectors are, the data points that lie closest and help you determine the position of the decision boundary. Let's move on. Whoa, okay, so that's the first time there's been quite a bit of change in the leaderboard. All right. So now, which of the following is true about bagging? I'll go to the full question view. Again, I'm glad that most of you have gotten the answer right, but let me just try to help you understand the whole picture here. So, okay, which of the following is true about bagging trees? In bagging trees, individual trees are independent data. From the data, you take a subset. Let's say you take like, am I audible? Can someone like reply in the chat if I am? Because it says bad internet network here. All right. Okay. Yeah, all right. I'll just start this explanation again then. So then bagging, what happens in bagging? You have a training data. Now from this training data, you basically take some subsets. Let's say you take 5 subsets. So you run those 5 subsets through 5 separate models. Now, all these models could be the same. So when I said bagging trees, what I meant is all of these 5 models are decision trees. So in bagging, what you do is that you run it separately. So you run all of these, like all of these trees separately. So you take that subset, you run that, give that subset to a tree, and all of those 5 trees run in parallel. So you have 5 subsets, you give it to 5 trees, and that happens all at the same time. So the individual trees are independent of one another. That's correct. And bagging is a method for improving performance by aggregating the results of weak learners. So that's what we learned. Each classifier, each tree is called a weak learner. When we aggregate the results of these learners, we get one final output. So that's what bagging does. So 1 and 2, both of these answers are correct. Now, so the next question is about boosting. And let me just explain boosting. So maybe it will help you answer the next question. So boosting is an algorithm where, again, you take a subset. But let's say you take 5 subsets. So actually, you initially start with just one subset. You take that one subset, you pass it through an algorithm. Now, after you pass it through the algorithm, you find out where has it been misclassified, where this algorithm misclassified the data points. So you take those misclassified data points as well as some points from the original data set, create a new data set and run it through another algorithm. So it works sequentially, not parallelly like bagging used to do. Finally, all the outputs are aggregated, but it works sequentially. So let's move on. All right. So the correct answer is actually just 2. So what I mentioned previously, here you don't have independent learners. So the first option says in boosting, individual weak learners are independent of each other. That's not true, because here you're running them sequentially, not parallelly. So the errors of one weak learner influences how the second weak learner performs. So that's how it works. It doesn't work like, just individual weak learners don't run independent of one another. How one weak learner performs, it affects how the next weak learner performs, because once you take a subset and pass it through one learner, let's say a decision tree, it misclassifies some points. So you take those misclassified points as well as some actual points from the data set, make another subset and run it through another algorithm. So the second classifier actually learns something from the first classifier. It depends on the errors of the first classifier. So that's why they're not independent. They run sequentially. They don't run parallelly. So when it's parallel, it's independent, but they're not parallel. So it is not independent of each other. But even boosting is a method for improving performance by aggregating. So in the end, you aggregate all the results. So that's the case here. Let's move on. All right. So, okay, that's great. So most of you have given the answer correctly. Let's go to the full question view and look at the full question. So in a random forest, let's say you generate hundreds of trees and then aggregate the result of these trees. So this is again classic example of the bagging ensemble learning. Which of the following is true about the individual tree in random forest? So one individual tree. So when you're reading this question and when you see random forest, you just got to relate it back to the concepts of bagging. So we just spoke about bagging before. So let's look at bagging and I'll try to understand this. So option number 1, individual tree is built on a subset of the features. That's absolutely correct. So individual trees are built on a subset of the features. Option 2 is the opposite of that. So individual tree is not built on all the features. Each individual tree is built on some subset of those features. Now 3, individual tree is built on subset of the observations. That is also true. So each individual tree will be built on the subset of the observations. We don't take the full set of observations to build a single tree in a random forest. We only take a subset of the observations. So you have features as well as observations. So by observations here, they mean the data points. So you take only a subset of the data points, and the subset of the data points can be with replacement, and you take a subset of the features. So suppose you want to detect heart attack or not. And to detect heart attack or not, you have features like chest pain, arm pain, let's say headache. And then you have like some 5 data points. So a subset of data points would be a subset of observations would be subsets of these 5 data points, and subset of features would be just if there are 5 features, you just take 3 or 4 out of all the 5. So the correct answer was 1 and 3, and most of you got this right. So good job. Let's move on. All right, the leaderboard remained exactly the same. And the answer for this actually is a decision tree. So if bagging has no, so when we're just coding out bagging and we're not assigning any estimator to it, by default it has a decision tree. Now random forest uses the concept of bagging. So in random forest is an example of a bagging algorithm. You can't have random forest as an estimator. You need estimator here means a learner or a classifier. So what do we do in random forest? We take multiple decision trees and combine it. So in bagging, if there is no estimator assigned by default, we use a decision tree because you don't use a random forest. Random forest is a combination of decision tree. Random forest is the bagging. So if there is no estimator assigned, if there's no classification assigned, then you add each estimator as a decision tree, and each of these decision trees combine together to give you a random forest. So random forest is just an example of the bagging algorithm. You don't use random forest as an estimator. You don't use random forest as a classifier. You use decision trees there. So that is the answer. All right, next question. Okay, once again, the leaderboard remained as is. And okay, which of the following is true about ensemble, average ensemble? So what does the first option say? It can only be used in classification problem. It can only be used in regression problem. No, that's not true. It can be used in both. So in classification, when the class, so there are two different types of classification. One is a hard classification, where it's either A or B. It's 1 or 0. Another is a soft classification. Soft classification is based on probabilities. So there's a 95% probability that it's A. There's a 5% probability that is B. Based on the higher probability, you assign it to be A. So when it's that type of a classification, a soft classification, where you're relying on like 95% and 5%, you use averaging. And definitely regression basically helps you print out a numeric value. So you will definitely use averaging. So averaging can be used for both classification as well as regression, because you're trying to print out a number here. And the number can be like, if it's soft classification based on probabilities, use it in classification. And regression anyway outputs a number. So you use it in regression as well. So that's the correct answer. And it's amazing that most of you have gotten it. So good job, all of you. Let's move on. All right, the leaderboard significantly changed this time. And okay, the question is, can a confusion matrix be used for regression tasks? Most of you have answered no, and that's absolutely right. So confusion matrix cannot be used for regression tasks. Confusion matrix helps you find things such as accuracy, recall, precision, F1 score. All of these metrics are things we use to evaluate classification tasks. For regression, we have more of mean square error, root mean square error, R square, and things like that. That is what helps you evaluate a regression task. But for classification, we use confusion matrix. Confusion matrix is like the basic evaluation metric that we use for classification tasks, not for regression. So from a confusion matrix, you can find out accuracy, you can find out precision, you can find out recall, you can find out the F1 score. So confusion matrix cannot be used for regression tasks. Let's move on. Okay, great. So before we discuss this question, I'll just go back to Jessica's comment about the previous question. So Jessica mentioned that it can be that the confusion matrix can be used for logistic regression, but I guess that's classification. And Jessica, that's absolutely right. So logistic regression is used for classification. So when I mentioned regression tasks, when I said the word regression tasks, I mean tasks or algorithms that perform regression. So regression is the task of printing out an output as an integer value. Classification is the task of printing out an output value that's a particular class. But regression is printing out like a numeric value as the output. So that's regression. And logistic regression, although it has the name regression in it, it's used for classification. And if you put it in different classes. So that's logistic regression. And for logistic regression, since it's a classification task, that's what it performs, we use confusion matrix. Now let's come to this question. If you just read the name, you'll be able to figure this out. False negatives. So false negatives are those that you actually predict negative, but that's wrong. It's actually positive. False negative. It's falsely accused as negative. It's actually positive, but falsely we're accusing it as negative. So you can think of it in that manner. So most of you have gotten this right, and that's absolutely amazing. So 2 more questions to go, and let's move on. Sorry. So when does a neural network model become a deep learning model? So again, most of you have gotten this right, and that's absolutely amazing. So neural network model becomes a deep learning model when you add more hidden layers and you increase the depth. So what is deep learning? Deep in deep learning stands for adding more layers. So if it's just one single neuron, it's just, neural network. You just have one layer. You have some interconnected neurons. In that case, it's a neural network. But as you increase the hidden layers, so let me just quickly draw up what this looks like. So if you just have neurons that are connected like this, that's just simply a neural network. But you have more layers and they're connected in this manner, let's say like this. You have more layers, you have more layers here, and that's connected in this manner. Then it is known as a deep neural network, because this is one layer and this is another layer. So you have two different layers. You may have more layers. So when you increase these layers, it's called a deep neural or a deep learning model. And that's what it is. So when you add more hidden layers and increase the depth, it's called a the neural network becomes a deep learning model. So that's about how a neural network becomes a deep learning model. On to the last question. All right, wonderful. So, okay, so which of the following is not an activation function? That is the answer. So some of you have put in hyperbolic tangent, and okay, let me just explain. So Relu stands for rectified linear unit, and this is an activation function. So what does an activation function do? Basically, an activation function is one that helps you learn or helps you model all the different inputs of a neural network to an output. So to learn and understand a little bit more about activation functions, do watch the recording of our previous session. Everything about an activation function is explained in detail there. Now, Relu and hyperbolic tangents, they are non-linear activation functions. So they do help you aggregate all the inputs you have to give you an output. That's what that's what you want to do with an activation function, right? So Relu is a type of non-linear activation function, and so is hyperbolic tangent. It sometimes referred to as tan H. A hyperbolic tangent activation function is referred to as a tan H activation function. And now linear is also an activation function. So linear is just that, a straight line is also an activation function. It's just that it does not model any non-linearities. That is definitely an activation function. But there is no activation function by the name of logistic. So logistic there's nothing called logistic. There is no activation function in itself. Logistic regression uses the sigmoid function. So sigmoid is an activation function, but there is no logistic, there is no function or activation function known as logistic. So that is the right answer. Logistic is not an activation function. Relu and hyperbolic tangent, which is also known as tan H, are non-linear activation functions. Linear activation function, as the name suggests, is linear. It could be a line sort of function. So that's it. And yes, we shall, that was the last question. Let's have a final look at our leaderboard. So Claire, Akansha, and Garima, congratulations, guys. Amazing job done. You guys were the top 3 scorers, and wonderful, wonderful job. Big claps to all of you, and big claps to everyone else who attempted this, because whoever attempted this, whether you knew something in ML or not, all of you tried in some way, and that in itself is so amazing. And you guys got so many answers right, and hopefully the ones that you got wrong you were able to understand in today's session. So thank you all so much for being an active part of this entire ML series. Hope you had some fun and hope you learned something. And yes, so we do have the recordings for all the sessions. And if you do, please do join the ML groups, study groups of the both Python as well as data science Slack, because there I have bookmarked the link to the Google Drive as well as recordings. So link to the Google Drive has all the data sets, the code files, as well as the slides for each session. And the recordings link is where all the recordings for all the sessions will be posted. So please do join the ML study group Slack channels. You can ask your doubts for this session, or if you missed the previous session and you watch the recordings, you can ask the doubts pertaining to the previous sessions, anything of that sort you can ask there. And yeah, that's it. So that's a wrap on our entire ML session, ML series. So it went on for very long, and thank you all so much for being an integral part of this. So if anyone has any doubts or anything to ask, you can feel free. Otherwise, the session has ended. Thank you all so much.